Hi folks, welcome to our first YouTube live session for Calculus 1. We're going to work a series of limit problems and kind of discuss those that you might have struggled with in the homework and whatnot. And if you have any questions along the way, there's a chat box over on the right hand side of your screen. Oh, depending upon what screen you're using. The chat box appears somewhere on your screen, and you can ask questions there at any point in time, and I'll try and address them. Just be aware there's a little bit of a delay, so you might have a little bit of drag time before I see the question, but that's okay. I'll come back to it whatever point I see it pop up in the chat window. But usually there's about a 30-second to a minute delay in what you see and what I'm producing. So without further ado, let's go ahead and get started. We want to evaluate the following limits. That's going to be the focus of today. And so the first one we're going to talk about is this limit as x approaches 9 of 3 minus square root of x over 81 minus x squared. How do we go about doing this? Well, the first thing you should always try is plug in. And so if we plug in, we get 3 minus the square root of 9 all over 81 minus 9 squared, which equals 0 over 0. And now I've seen quite a few people talk about, well, does this mean that it just doesn't exist, or is it going to a certain number, or what's actually happening? Well, actually, when you have 0 over 0, that's what we call an indeterminate form. Okay, so that being an indeterminate form means we don't have enough information. So we're going to need to work with the problem a little bit. And this is one of the types that, and we're going to tie in two parts here that I want you to see. So what makes this difficult right now? Well, normally we could kind of factor things, and so for example, we could rewrite this as the limit as x approaches 9 of, well, the bottom factors nicely. It's 9 minus x and 9 plus x. But that 3 minus square root of x, that looks kind of pesky right there. And so how do we fix it? Well, the key to fixing this happens to be this magical word called conjugation, right? And the underlying principle behind conjugation, so let's say you have a factor of a minus b, okay, which is what we essentially have there. Granted, you see a square root of x and all that stuff. But if we multiply by a plus b, you get a squared minus b squared. So if you take a look at this, you might say, okay, whoopity-doo, what does that do for us? Well, in this case, notice if we square that square root, all of a sudden we'd have things work out nicely. Now, but we can't just multiply willy-nilly. So what the conjugation method that we're using for limits here is we actually have to multiply not just on the numerator, but we have to multiply by the same thing in the denominator. So the reason why is what we just multiplied by is 1. So that's an equivalent fraction to what we had in that first line. So since we haven't changed the fraction at all, we're still good. What I see a lot of people do is they'll just square where they want to. So they might just square the x and square the 3 and say, oh, we're good. It doesn't work like that. So you got to worry about when you see a square root, these are for finite limits. There's going to be a different rule for infinite limits coming up. But for finite limits, you can do this conjugation trick, and it works over and over again. Now, what does it do for us? Well, notice if I let a be 3 and b be square root of x, what happens? Well, this is 3 minus square root of x, 3 plus square root of x. So that should be 3 squared minus the square root of x squared, right? And that's the whole reason conjugation works. It's basically we have a difference of squares is what we have. And so what we'd get is this becomes just 9 minus x, which is a beautiful thing. That's exactly what we want right there. So if you take a look, where can we go from here? We get the limit as x approaches 9. We know the numerator now becomes 9 minus x, okay, and then the denominator you get 9 minus x, and then we get a 9 plus x. Oops, sorry, I got a little ahead of myself. 9 plus x, and then finally we'll toss in that factor of 3 plus square root of x, which we couldn't really multiply anything there. Now the next rule limits, why we're starting off with conjugation, is so we can kind of get 2 for 1 all in the same spot. We could try plugging in again. Okay, so but if you plug in again, notice you'll get 0 on top from the 9 minus x, and you'll get 0 on the bottom from the 9 minus x there. Oh, so we're stuck again. Well, actually no. So here's where we can simplify some more and make things so 0 over 0 indeterminate form. We got to work with the limit a little bit more. So we go limit as x approaches 9 But what happens? Well, we can take those 9 minus x's and they cancel. Right? What's going to happen in the graph is you're going to have a hole when x equals 9 because of how that works. So what we have left up top is just 1. And then what we have down below is 9 plus x times 3 plus square root of x. Okay, well that's a beautiful thing right there, because now we can plug in. Notice we get 1 over 9 plus 9 is 18. Well, actually, let me write out that step. I'll start to skip these steps later on as we progress, but just so you can witness what's happened, we go 9 plus 9 and 3 plus square root of 9. Okay, so now what happens? You get 1 over 18 times 3 plus square root of 9. The square root of 9 is 3, so that's going to be 3 plus 3 is 6. Okay, so what is that? 60 plus 48 is 108. So this is 1 over 108. And you can leave it as 1 over and then put 18 times 6 in the denominator. That's just fine too, by the way. But we get 1 over 108. So what actually happens in terms of the graph? Now, I'm not so sure what happens on the other sides. But to give you some representation, you have 9 way over here, and then you'd have, this isn't going to be to scale at all, but you have 1 over 108. In terms of the graph, right here you're going to have a hole, and so I'm not sure which way this graph is going, but so you'll have lines on either side, something like that. So this is the underlying theme that we're going to get to, tying the graphs in with the equations and all that stuff. But the whole idea of limits, this tells us, okay, since this limit exists and it's a number, but when we plug in the number, we got 0 over 0, meaning it was undefined on the original function, you have a hole in the graph. So when we approach it from the left, we approach it from the right, it's actually hitting that 1 over 108. So if you have any questions, once again, there's a chat box appearing. Please ask those questions in there, and I'll be happy to answer them along the way. But I don't see any questions at this point, so I'm going to move on to the next one. Okay, so moving forward. So our next one, this looks really scary, but these ones are usually a lot easier. The limit as x approaches 3 of square root of g of x, given that limit as x approaches 3 of g of x equals 8. So this one a lot of people struggled on. The nice part is, though, this square root business in this case is a constant. So here's the cool trick that you can do with the limit. So we have, first off, I'm just going to rewrite that first equation, or expression I should say. So with this being a square root, that's just a basically g of x raised to the 1/2 power, so that's just a constant power. So what we can do is take this limit inside the square root. And so all this becomes now is just the square root of, well, we know that limit right here. Limit as x approaches 3 of g of x equals 8, so this is square root of 8 and you're done. Simple as that. Yeah, so there's really not much more to this. It's just a matter of you can move limits around inside functions and all that. You'll learn later if you have essentially, let me use, instead of g, I'll use f and h. If you have f composed with h of x, and you have the limit as x approaches some constant c, and I'll say, we'll learn about continuity a little bit later too. If f is continuous, the big theme here is that you can take that and just look at the limit of the inside function and then just apply it to the outermost function afterwards. And that's essentially what we did here in general. So that's a big result that we'll use over and over again. You'll actually touch on it even more when we get to the continuity section, but this is kind of leading on up to that section coming up there. So, all right, 2 down, only a handful more to go. So this one gave a lot of people quite a bit of difficulty, so I want to try and go through it and how do we work this. So I think what freaks out a lot of people in this is you have the y approaching t, so that looks scary, right? So let's talk about that. I'm going to do a couple other problems, and the way we'll approach it, we'll take y. Remember, our variable always appears in the first position, like right there. So we'll still have y, but let's have it approach a couple different values. We'll do limit as y approaches 2 of, in this case, this is y cubed minus 2 cubed over y squared minus 2 squared. And we can also do, say, limit as y approaches 3 of y cubed minus 3 cubed over y squared minus 3 squared. Let's take a look at both of these and see if we can catch a trend, and then maybe try and build to something bigger, right? And that's the idea with a lot of them. You're actually going to just try and work some examples and see if you can get a feel, and then maybe you can try and go to that more general example, which now, if we can solve the general one, we can solve pretty much any one of them. And I'll show the importance of it in a minute. So in this case, notice when you plug in 2, so you get 2 cubed minus 2 cubed over 2 squared minus 2 squared equals 0 over 0. So what does that tell us? Well, that tells us in this case that we have an indeterminate form, so we're going to have to do something with this. Okay, so what do we have to do? Well, let's take a look. When taking a look at this one, we have y cubed minus 2 cubed and y squared minus 2 squared. We plugged in 2, we got 0 over 0. So what that actually tells us is something much larger, since we have polynomials in these cases. When you have polynomials rather than the square roots, it tells you what the factor is. So our factor sitting in both of these is y minus 2. Now the one down below is probably a little bit easier to factor. You get y minus 2, y plus 2. The one up top you might not know. So the difference of cubes, right? So we actually already touched on the difference of squares. And that was, so difference of squares would be something like x squared, or let me do it a squared minus b squared, since we are using a y here. A squared minus b squared equals a minus b, a plus b. Okay, difference of cubes, you get a cubed minus b cubed, and that should equal a minus b. Notice we still have the factor, a minus b. And then it goes a squared plus ab plus b squared. If you don't believe me, try and expand this out. You take a times each of the 3 terms, and notice you have positives, and then you'll take negative b times each of the 3 terms, and notice you'll have negatives associated with those. You'll see a lot of stuff canceling out in the middle, and that's why that works out that way. Okay, so using this to our advantage, we have y cubed minus 2 cubed. So what does that mean? Well, it means we have y squared plus our a is y and our b is 2, so you get y times 2, plus our b squared is just going to be 2 squared. Okay, let's take a look at the one over on the right hand side. Notice we still have a similar scenario. This is just y minus 3, y plus 3. And in our other scenario, when you plugged in, oh, I should be careful. The reason why, when you plug these in, why we can say that real quick, why we know right away that's going to happen, because you have 0 over 0. Right, since we had 0 over 0, that's the reason why we can say that y minus 3 is a factor of both the numerator and the denominator. And now we can use those formulas if you didn't recognize that. So we have y times 3 plus 3 squared. By the way, there's a difference of quartics, difference of quintics. You can do this formula on up. It's really not too bad. Just you can kind of see the trend here, though. You have a plus b, and notice all those terms seem to be plus when we have a difference going on. The next one, a squared plus ab plus b squared. The next one would be, if you had difference of quartics, it would be a cubed plus a squared b plus ab squared plus b cubed. That's essentially what's happening all the way on down. So you can build all those up. So now, and if you don't know that, the other way, if you'd like to see it, I'm happy to show you too. If you know one of the factors and you don't know how to factor the rest, the other way is polynomial division. If you want a refresher on that, I can show you that as well. So there's a couple ways to kind of approach this. But moving forward from here, where do we go? Well, we get limit as y approaches 2. Well, notice what happens. You have the y minus 2's cancel. Because we had 0 over 0, they should cancel, right? And what are we left with? We're left with y squared plus, I'll rewrite that as 2y plus 2 squared is just 4. And in our other case, we have y plus 2. So notice this makes, when we plug that in, we'll get 2 squared plus 2 times 2 plus 4. So now that's 4 plus 4 is 8 plus another 4 is 12 all over 2 plus 2, which is 4. So you get 12 over 4, which our final answer was 3. Okay, yippee. So now in our other scenario, let's look at the limit as y approaches 3. We already saw it. We use a difference of cubes and all that jazz. So this thing equals the limit as y approaches 3 of, we have y squared plus 3y plus 9, and then y plus 3. The reason why, the y minus 3 is canceled. Okay, so what happens? Well, we get 3 squared plus 3 times 3 plus 9. Okay, all over y plus 3. So notice what happened here. Well, we have, in this case, this was 27 up top and 6 down below. Notice both of those have a common factor of 3, so we'd have 9 over 2 is our final answer. But notice in every shot, though, you had the extra factors of 3 going on there. The big thing is, though, with each scenario, we used a difference of cubes and a difference of squares. So let's try and generalize this. Limit as y approaches t. We know how the bottom's going to behave because we have that t in that second spot, so you get a y minus t, which when you plug it in, notice you had t cubed minus t cubed all over t squared minus t squared. That was 0 over 0. That was our big indicator that we had a y minus t as a factor of both the numerator and the denominator. Now moving forward from here, where do we go? Well, we get y minus t, it should be y plus t. Okay, and then in the numerator we should have y squared plus y times t plus t squared. Okay, so now we got a factor. Now I'm going to erase this stuff down below, and then I'll actually show you the usefulness of this. Okay, so this becomes the limit as y approaches t. The y minus t's will cancel, and you're left with y squared plus y times t plus t squared all over y plus t. And then maybe we can start to see what the trend is. Now notice our y is the variable, so we have t going in for all those y's. So you get t squared plus t times t plus t squared. And you might recall I mentioned, hey, there's this 3 that happens here every time. The reason why, t squared plus t squared plus t squared, there's 3 of those t squareds all over 2 of the t's. Okay, so at the end of the day, what happens? Well, one of your squares will cancel off with the term down below, so that square cancels off with that t. And so what we're left with is just 3/2 t. So just a little FYI, when we did limit as y approaches 3 of y cubed minus 3 cubed all over y squared minus 3 squared, notice we got 3/2 times, what is our t value? Our t value is 3. So 3/2 times 3, which equals 9/2, so it matches. To extend a little bit further, you can see how this formula goes. Let's do limit as y approaches 5 of y squared minus 125, oh sorry, y cubed over minus 125, and then we have y squared minus 25. What actually happens in this case? Well, you can recognize hopefully fairly quickly that this is the same thing as limit as y approaches 5 of y cubed minus 5 cubed over y squared minus 5 squared, which is exactly the type of scenario that we dealt with up there. So our t value is 5, so this should just be 3/2 times 5, which equals 15 over 2. Notice that took us a matter of a few seconds versus having to go through the whole rigmarole of, okay, we got to expand this or factor this, and then cross out the terms and all that stuff. If you know the formulas, you can start to work them out really quick. So hopefully that makes sense on that problem and seeing how that works out. A lot of people struggled on that one, so I just want to make sure we got that down. Alright, and next problem that you'll see happen over and over again that a few of you weren't catching right away. So in this scenario, notice when we plug in 0, we get 0 times sine of, this is 5 times 0 plus 2 over 0. Well, notice this thing is going all over the place. So this is we don't know. And if I take a 0 times we don't know, it's not a constant. We don't know what this limit is. So this is an indeterminate form. So that means we're going to have to work with this one. You are not going to be able to factor, though, because of the sign. You can't just factor out theta cubed outside, right? So it doesn't work like the other ones. So what do we have at our disposal? Well, the key is the sign. The sign function is actually bounded, okay? And that's important. So what we can do is we can bound sine of whatever this junk is. Who cares what it is on the inside? But we can bound it between -1 and +1. Okay? So I'm not saying that this will always work for sine, but this is one of the key components when it's undefined on the inside. Okay. Now from here, well, we can actually start to work with this a little bit more. We can say, okay, if we have negative, and we'll take -1 times this theta to the 7th, and I'm going to put an absolute value here. The reason I'm going to put absolute value, if you multiply by negative, it switches the inequality. So I'm going to make sure that's a positive number all the time. So -1 times theta to the 7th is less than or equal to theta to the 7th times sine of 5 theta plus 2 over theta cubed. And that's less than or equal to an absolute value of theta to the 7th. Now, technically I should put this absolute value here, but we'll be able to drop it if we I'll kind of show how we can work with this. So another way we could work with this is if you wanted to do theta from the right hand side, you could go negative theta to the 7th, but since it's from the right hand side, that's positive, so we're in good shape. We still have the same inequality. So theta approaching 0 from the right hand side of, this is just theta to the 7th sine of 5 theta plus 2 over theta cubed, and that's less than or equal to the limit as theta approaches 0 from the right of theta to the 7th. Okay, and if we approached it from the left hand side, here's what happens. Notice we're talking negative numbers now, right? It's different if we were approaching another number besides 0, but 0 is kind of the point where you switch from negative to positive, so I want to make sure that we're all aware of that. So then what happens in that case, you go this direction. And that's greater than or equal to, limit is theta, which is 0 to the left, theta to the 7th. Okay. So now we have all that information there. What does that do for us? Well, what's the limit as theta approaches 0 of negative theta to the 7th? If we approach it from the right, doesn't matter, it's 0. And then our right hand side is 0. So basically what this has done is that means this equals 0 by the squeeze theorem. In a similar manner, we have our left-hand side down below is equal to 0, our right-hand side is equal to 0, so basically we've squeezed this thing, and that equals 0 by the squeeze theorem. So at the end of the day, and as I said, you could be a little bit more lax and just drop the absolute values from the get-go. We get the limit as theta approaches 0 of theta to the 7th sine of 5 theta plus 2 over theta cubed. That whole thing equals 0 by the squeeze theorem. And then I added in one extra. There's one extra part that actually allows it to be by the squeeze theorem. Notice our left-hand limit and our right-hand limit are equal. Right? You always need the left-hand limit and the right-hand limit to be the same in order for those the limit to exist. So we had that happen. We're good to go. Any questions on that one? That one's kind of tricky, so I know where we can have some things fall apart here. Okay. So no questions on that one. We'll keep on moving forward. Alright, so now taking a look at the piecewise functions. How does that work? Well, with the piecewise function, we have this x minus 5 for x less than or equal to negative 1, x squared plus 2 for negative 1 less than x less than or equal to 1, and then 4 plus 3x for x greater than 1. So in our first scenario, notice we're approaching negative 1 from the left. So this would be things like negative 1.00001, and we keep on going. So what scenario would that be in this case? Well, notice if we're less than or equal to negative 1, we're in this first scenario. So what that means is all we're going to do is just take this and plug it into that first scenario and see. Hopefully we won't get a 0 over 0 scenario. And notice we don't. So our answer just becomes negative 6. So basically it's like picking which function to plug it into and going from there. Okay, so our next one. If we approach negative 1 from the right, so if we do that, a number that we're kind of really close to, you could do negative 0.99999, so on and so forth, right? Just for an example. I'm not saying that you can plug it in and get your answer right away. It's just a good way to approach it. So notice that would fall into our second scenario because that's between negative 1 and positive 1. Okay, so then we have to use that second equation, plug in for x. But we're plugging in negative 1, no different there. So you take negative 1, we're going to square it, and then we add 2. Well, negative 1 squared is 1, plus 2 is 3. And we're done. Okay, next scenario, limit as x approaches negative 1. Well, notice if that's to exist, we need this to be equal for limit as x approaches negative 1 of f of x. But notice they aren't equal. So what does that mean? That means this is a does not exist scenario. If they were equal, it'll just be the number of those both sides. Okay? So now our next one, limit as x approaches 1 of f of x. Okay, so you might say, okay, we plug it into the left, the one where we had the equal. Well, that doesn't quite work for us. Actually, all we have to do is we'll have to figure out limit as x approaches 1 from the left of f of x. And notice that equals, if we're approaching 1 from the left, it will be this second equation right here. And so that would be 1 squared plus 2, which equals 3. And then we'll also need limit as x approaches 1 from the right of f of x, which in that case we will be down to our third scenario right there, which is equal to 4 plus 3 times 1, which equals 7. Okay. So notice these two not equal. So this is also a does not exist scenario. Alright. Last but certainly not least, f of negative 1. So that one we do just look at the value. We don't have to worry about the numbers that are close by or anything like that. So we're just going to use the second equation. And we already found this actually before because it happened to be our limit as well. So you get negative 1 squared plus 2, which equals 3. And those are all your final answers. So you have 3 does not exist, 3, and -6. Okay, I know that piecewise functions look scary, but as soon as you find out which category they fall into, in terms of that, you're just plugging in. And 9 times out of 10, unless you have a 0 over 0 scenario or something where it's undefined, you're going to be able to find your answer pretty quickly in those. Okay, so the other part that gives people trouble is graphs. So evaluate the following limits. We have a graph right here. Assuming each of these, if you don't ever see an indication as to, oh, we do have a -10 and +10, so each of these grid marks is 1. So that's nice for us. So the first scenario, what we're going to do is we're going to go -5 right there. You can kind of see that hash mark that I put there. Well, so notice in order for this to exist, you need the limit as x approaches -5 from the left of f of x. Well, what is that? Well, notice as we approach this, and actually what I'll do is just to illustrate a little bit more, I'll draw -5 all the way up and down. And so on the left-hand side, we're trying to find the y value. Well, notice the y value would actually be -2. And the limit as x approaches -5 from the right would be on the right hand side of this. So what y value are we approaching here? Well, that's 1, 2, 3, 4, 5. So that would be 5. Notice these two are not the same. So we have a does not exist scenario going on right there. Okay, so we have that part. And you can see that from the graph. When you have a jump, like from one end to the other, you aren't going to have the limit exist. You have to do left and right hand limits. Okay, for our next one, we want to do 5 from the left and right. So what we'll do, we'll go and mark it. 1, 2, 3, 4, 5. And now I'll draw a vertical line, just so we know which side of this vertical line we're going to be on the graph. Oh, and by the way, you don't see it written right here, but this graph is f of x, obviously. That's what we're kind of working with here. So now when we approach that line from the left-hand side, so we're approaching from this side, we want to see what this y value is right over here. So notice we've gone up 1, 2, 3, 4, 5, 6, 7. So 5 from the left is 7. And 5 from the right, what y value are we approaching when we're going from this side? Well, notice we get to this point right here. And that's 1, 2, 3. And so the graphs go a little bit quicker, at least I like to believe so, a little bit quicker than the other scenario where you have the piecewise function. Right? You can kind of look and hopefully break these apart. So now our next one, limit as x approaches -2 of f of x. So we'll have to do a left and right hand limit until you get in the habit of it. So -2 from the left of f of x. So notice here's -2. From the left-hand side, notice we're coming to that value. Well, the y value that we're approaching, notice it's an open hole, but that's okay. Doesn't matter. It's still just +2. We're talking about where we're approaching, not the function value itself. On the other scenario, where are we approaching? Well, from the right-hand side, we're coming up to that point right there, and notice that's the same y value. That's +2. Notice our left and right-hand limits are the same in this case, so we actually get a limit being +2. Holes in the graph produce a limit. So that's a big takeaway. If you have a hole in the graph versus a jump in the graph, a hole will give you a limit. Okay? So keep that in mind, even though the function value appears elsewhere. So now the rest is just function values. So f of -5, where do we go? Well, we go for that solid dot right there, because there's -5. We found out where it intersects. And then we look at the y value associated with that solid dot. And that y value is 1. So that's all this is. This is college algebra stuff right here. And then our next one for -2, there's our solid dot. And there we go. We go down 3 units, so that's -3. Questions on the graph. That's something you will see again. I promise you that. You'll see it over and over again in many different forms. And so I want to make sure you see a couple graphs, how they're worked out and stuff like that. So any questions on that piece? Please, and that's what I'm here for mainly, is asking. I want to answer your questions when you see stuff pop up and whatnot. So another one that we kind of had some trouble on Find the limit as x approaches 8 of f of x if 3x plus 40 is less than or equal to f of x, which is less than or equal to x squared on the interval 6 to 10. Notice 8 is in here. That's good, right? Because what that means is we can just slap a limit as x approaches 8 on all three sides and see what happens, right? So this is limit as x approaches 8. So this problem had the work done for us. This was in the homework. So, and limit as x approaches 8 of x squared. And only I think it was something like 58% of the class was able to get this one. So I want to make sure we kind of hit this home. So notice we plug in 8 on this one side, so you get, just so we can do it up above, 3 times 8 plus 40. Notice that's going to be 64. And in this case, you get 8 squared. It's going to be 64. Hey, they match. What do you know? 64 is less than or equal to this limit in the middle, which is less than or equal to 64. So what does that mean? At the end of the day, that means that the limit as x approaches 8, if you have a number between 64 and 64, I bet you I can guess that number, and I would think it would be 64. And that's exactly what our answer is. Just to hit the point home by the squeeze theorem. Okay, make sure you're aware of how to use that squeeze theorem. Make sure you're aware of showing the steps. That's a big thing too. Being able to show that extra work on how you work those out with the squeeze theorem, that's important as well. Okay, so this is the one that scared a lot of people. And so let's talk about this and try and drive this point home. So first off, limit as x approaches 1. Let's see what happens. Well, a lot of people got these parts. So notice we go x approaching 1. We got to go from the left and right. Notice there's a jump in the graph, so that means this is a does not exist scenario. Okay, so done there. If you want more of an explanation, notice the left-hand limit as x approaches 1 would be 0. The right-hand limit would be positive 1. So, hopefully we're getting that down. Now the next one, I know you can't see it with it being the y-axis there as well, but as we approach 0, from the left, notice that y value is negative 1. From the right, notice that y value is 0. And we come up with our answer there. Limit as x approaches 3 from the left and right. 1, 2, 3. Okay, from the left-hand side of that line, notice our y value is 2. From the right-hand side, notice our y value is 3. Okay, I'll do one more. Limit as x approaches. So notice we have a from the left-hand side, where a is an integer. So I'll do negative 2 from the left. So negative 2 from the left. So notice what happens. Well, we're down at this y value. We've gone down 1, 2, 3 units, so that's negative 3. Huh. So let's take a closer look at some of these. Actually, I'll switch this to black. Notice we had 0 right here, and we come up with negative 1. Well, the way to do that is we go 0 minus 1, right? On this 3 from the left, we get 2 right here. Notice a way to do that. We go 3 minus 1. We're just taking away 1 unit. From negative 2 from the left, notice that's the same thing as negative 2 minus 1. So if we have an integer, and we approach it from the left, I'm not saying this would work always, but when you look at the graph, notice there's some symmetry going on here in terms of the shift, right? You're only going up 1 unit at a time, or going down 1 unit at a time. So that's the beauty, is the graph it gives us to us. Now, technically, we should extend a little bit further. I think your problem said where the interval's from negative 3 to positive 3, and that would make it a little bit easier as well. Then we can actually answer that correctly. So, but let a be an integer, determine the limit as x approaches a from the left of f of x. What do we do here every time? Well, we take a, and we subtract 1. That's it. Okay. If you actually wanted to toss in, I think the other one that some people might want to see is limit as x approaches a from the right, f of x. Notice here you have a 3 and then you have a 3. You had a 0 from the right, you have a 0. The general trend of what you see is those numbers match. So that means whatever appears down here, if it's an integer, it should be, when we're approaching it from the right, it should be that integer itself. Okay. And so I finished on that one. That was the one that gave the most trouble and questions in terms of the material. So I think that's a good place to stop. I don't see any questions. If there are any, please feel free to post them in the discussions, or tune in next time and you can ask questions or post in that YouTube Live questions discussion board. I'm happy to answer things in there as well. So wish you all the best. I hope you all have a good day, and hopefully this helped a little bit with those limits and whatnot.